Hello everyone, welcome back. This is an introduction video for self-balancing binary search tree type called red-black tree. Let's understand about it in a detail. Let's say we want to insert these values in a same order in a binary search tree, normal binary search tree. Then our binary search tree will look like this. Because in a binary search tree, we follow the property where for each node, the smaller values than that node value are added on the left side of that node, and the greater values than that node value are added on a right side of that node. And because of this insertion order, our normal binary search tree structure will look like this. Now, if we see, the structure of this binary search tree is not balanced because it is going on the left side, right? It is just going on the left side. That is why it is called as a left skewed binary search tree. It is an unbalanced binary search tree. Now, what is the impact of this? Because of this, the tree operations like search, insert, delete, they can take, in a worst case, O of n time complexity. N is the number of nodes in a tree. Let's say we want to search 50 in a tree, then we'll have to parse all the nodes in this tree, and then only we'll be able to find 50. So that's why the worst case time complexity for such structure becomes O of n. But generally in the binary search tree, we expect the time complexity to be log of n. But because of this unbalanced structure, it can go till O of n. Now we need a way to balance this unbalanced binary search tree. And that is what is supported in a different self-balancing binary search tree. And one of the type is red-black tree. Now, red-black tree is a self-balancing binary search tree to keep tree balanced and keep the time complexity of tree operations like search, insert, delete within log of n only. So using some of the properties, it makes itself self-balancing and tries to balance itself whenever those properties are violated, so that the overall time complexity of this tree operations will be within O of log of n. Now each node in a red-black tree has an extra bit of information representing its color, either red or black. So in a normal binary search tree or in a normal node of the tree, we know that it contains data and it contains the left and right pointer to point to left and right check. But in a red-black tree, along with that, it contains one extra bit, basically 0 or 1, right? To represent what is the color of node. Why? Because using this color properties only, it balances itself. We'll understand the properties based on which it tries to balance in the next slide. So it uses this coloring property and the rotations to keep itself balanced. Let's understand the properties of red-black tree. The first property is that every node in a red-black tree is either red or black. The root of the red-black tree is always black. The root of that red-black tree should be always black. The next property is that red nodes can't have red children. It means that no two red nodes can be connected directly to each other on any path in a tree. So the structure like this, where two red nodes are connected like parent-child, is not allowed in a red-black tree. For example, let's say if the 70 node is also red, then that is not allowed because 70 and 65 are directly connected to each other. That is not allowed. Two red nodes cannot be connected to each other directly. The next property is that all nilled leaves are considered black. So nil leaves means the null values like this. Basically, for these nodes, the left and right, or for this node, the right is null. So these nulls are basically considered as a black. The next property is that every path from node to its descendant null values must contain the same number of black nodes. and it is true for every node in a tree. Basically, let's say for 60, what are the path from that node to descendant null node? This is 1, 60, 50, this null, 60, 50, this null, 60, 70, this null, 60, 70, 65, this null. These are the path from 60 to its descendant null nodes. And if we see for each path, the number of black nodes are 3, right? 1, 2, 3, 1, 2, 3, 1, 2, 3. So it is true for every path. And that is what red-black tree property expects. And it is true for every node. Let's say for 50 also, there are two paths, 1, 2. And for both the paths, the number of black nodes are same, which is 2. The next property, basically, let's say if we see red-black tree property like this, red-black tree like this, is this the valid red-black tree? Let's see whether it basically satisfies the property of red-black tree. Every node is either red or black. That is correct. It is not, see here it is or. So it is not forced that both red and black should be there. So it is possible that all the nodes in a red-black tree are black. The root is always black. Now here root is also black. There are no red nodes, so which is fine. This is also fine. Now every path from node to its descendant null nodes must contain the same number of black nodes. Now here it is like 1, 2, 3, the null node 4. So it is true for every path and for every node. So that's why this is a valid red-black tree. So it is possible that in a red-black tree, all the nodes can be of black color. Now, is this the valid red-black tree? Let's see. Every node is either red or black. That is fine. The root is always black. But here the root is red. That's why it is not a valid red-black tree. And that is the reason we will not see the red-black tree where all the nodes are red in color. Because this is the property we need to consider, that root is always black. So this is valid and this is not valid. So this is one of the case where all the nodes in a red-black tree can also be black. Now, one more thing to note is that the new nodes, whichever new node we are going to add to our red-black tree, initially they are always inserted as a red node. Like we create a new node, so the color given to that new node is always red. It might change based on if the tree is unbalanced. Red-black tree might do the coloring and rotation and might change the color of that new node. But initially, the color of that new node is always red. Now, there will be question that we already saw AVL tree in a self-balancing binary search tree before. Then why do we need red-black tree, right? So let's understand the difference between the AVL tree and red-black tree. So let's say we have these two trees, right? Basically, it is the same tree. We are representing this tree here as a AVL tree, and we are representing the same tree as a red-black tree here. You can see values and everything is same. Now, this numbers here in a AVL tree, we know it is a balance factor, right? Basically, the height of left subtree minus height of right subtree. So this is the balance factor for each node. And it is within, basically, it is not violating the case like 0, 1, minus 1, what is expected in AVL tree. That based on that, this is a balanced AVL tree. Now, let's say we want to insert 45 here. Now, for new node, we know that balance factor is 0. Now, if we insert 45, the balance factor will basically change upstream, and we can see that tree becomes unbalanced at 70 because AVL tree expects balance factor to be 0, 1 or minus 1. Now it is greater than 1. That's why it is unbalanced. So now it is unbalanced. So in AVL tree, what do we need to do? We need to do rotations. Now it is the left right rotation. So in this case, we will require two rotations. Left rotate at Y and left right rotate at Z. So this is the standard rotations we apply in this situation, right? So the point is basically we require two rotations to make the tree balanced again in a AVL tree, just with a one insertion of node 45. Now let's say if we insert the same node 45 on a red black tree. Now we inserted it as a red node initially, the new node. Now is it still holding all the red black tree properties? Root is always black. No two red nodes are connected directly to each other. The number of black nodes on each path is same. So it is still basically satisfying all the red black tree properties. So we inserted 45, but it did not do any rotation or it did not require anything, right? We might say it is unbalanced here. So that is what the idea, right? Red black tree does not enforce the strict balancing. That's why we don't require the too many rotations, right? Every time we don't need a rotation like we see in a AVL tree, we require a rotation whenever the balance factor is violated, which is 0, 1, -1. So what do we understand from this? That AVL tree follows the strict balancing strategy. But red black tree, as we saw, it follows the less strict balancing strategy. It uses the color property, and it is possible that tree might be little bit unbalanced, right? So that is the main difference between AVL tree and red black tree. Because we saw that whenever we inserted the 45 in the previous tree, it had to do rotations because of the strict balancing strategy. And in red black tree, the rotations didn't require. Now in a AVL tree, there are more rotations because of this strict balancing, as we saw in the previous example. In a red black tree, the rotations are less because of the looser balancing based on this color property, as we saw in a previous example. Now, there will be a point that, okay, now if the red black tree doesn't have the strict balancing, then the height of the tree might be a little bit increased, right? Yes, that's why in a AVL tree, the search performance is slightly better than red black tree. In a red black tree, it is slightly worse than AVL tree, but the overall, it is still O of log of n, right? So in that case, basically red black tree is balancing between the too many rotations and search performance, but it is making sure that it is still within the log of n. It is still, it is slightly worse than AVL tree, but still within the log of n. Now, that is the reason basically AVL tree is more suitable where we need a where our requirement is for read heavy, means there are a lot of search operations are happening and not much insertion or deletion heavy. Because as we saw that because of this strict balancing, the rotations on a AVL tree are much more. And it can cause a performance problem if we have too many insertions or deletions, right? That's why if there is a requirement where insertion and deletion is less, but read is very, very high, then AVL tree is suitable. Now the red black tree provides the balance between search and insertion. So it is suitable when the requirement is both insertion heavy or deletion heavy along with the read heavy. It gives slightly worse performance than AVL tree for read, but as we mentioned in previous slide, that it is still within of log of n. So that's why it is suitable for both insertion, deletion heavy and read heavy requirement. Now, because of this balance which red black tree provides, in most of the libraries, like in a Java, whatever libraries you see, tree map or standard template library or in-memory database indexing, where we need to store the indexes in a memory, right? There, the red black tree is more preferred than AVL tree because of this balancing which is provided by red black tree, considering both insertion, deletion heavy and read heavy. So that is the reason red black tree came into the picture to solve this too many rotations problem in a AVL tree for insertion and deletion, like what we see in a previous example. Hopefully you might have understood about the difference between AVL tree and red black tree and what is the reason behind having red black tree also as one of the self-balancing binary search tree. So in this video, we understood about what is red black tree, how it basically it is a type of self-balancing binary search tree, tries to cover the limitations of normal binary search tree, the unbalanced normal binary search tree. And then we understood about the properties of the red black tree, and then try to understand why do we need a red black tree if we already have AVL tree, and how it is used in a real life cases like standard template libraries, in-memory database indexing, because of this proper balancing provided by red black tree. If you like the video, please share and subscribe. Thank you so much. In the next video, we'll cover about the insertion in a red black tree, and we'll understand how the balancing happens in a red black tree. Thank you so much.